I'm Robert Fisher. I'm an assistant professor of physics at UMass Dartmouth. And really what excites me about science is to discover how the universe works using the power of computation. The main research question we're trying to answer in our research is to try to understand essentially what the universe is made out of and what its long-term future will be. And we're working on a small piece of that. Astronomers have recently discovered not only is the universe expanding over time, but that the rate of expansion of the universe, to everyone's surprise, is actually speeding up or accelerating. And this was the subject of the Nobel Prize that was awarded in 2011. The primary tools that astronomers use to determine distances in the cosmos are what are known as standard candles. So imagine that you had a candle of a fixed brightness and you looked at that candle at different distances. The further away the candle is, the dimmer it will be. And if it's the same brightness, you can actually use that fact to determine its distance. Of course, we don't have candles in the universe, but we do have stars, and we have certain types of exploding stars, supernovae, that have about the same brightness. And that's the fundamental question that we're excited about answering, is what are the nature of a certain type of supernovae that are used as standard candles to measure distances in the cosmos. So one of the great mysteries surrounding the class of supernovae that we're examining is we don't really know what they are. It's a great mystery. Even though a Nobel Prize was awarded in the subject, the sort of amazing thing about the supernovae is that no one can really tell you exactly what they are. We know some things about them. We know that, for instance, like our sun will end its life eventually, in about 5 billion years, after it's finished burning all of the hydrogen in its interior, will eventually become sort of a dead cinder of a star, and that is called a white dwarf. And so, in some cases, a star, a white dwarf, at the end of its life, could be in orbit around another star and will lead to an explosion. The other possibility, and is quite an active area of debate here as to which of these is the correct model, is that instead of having one white dwarf in a system, you have two white dwarfs that come together and somehow coalesce or lead to a merger of some kind and will lead to an explosion. Which of these two models is correct is really quite an open mystery, and the stakes are extremely high because the understanding of these systems is directly connected to our understanding of the expansion of the cosmos. This is an amazing visualization that we're looking at of a merger process of two white dwarfs. The one on the left is then seen in red, and the one on the right is this green region, which is actually, the white dwarf has been disrupted in the incredible tidal gravitational field of its companion. And in this process, it's being gobbled up. The scale that we're looking at on both sides of this box are about 100,000 kilometers. It's larger than the size of our Earth, but not too much larger than that. And the time that we're looking at is over the duration of a few hours. Over those few hours, the companion white dwarf is slowly being gobbled up or accreted onto its companion seen in the red, and you can see it sort of spinning around in this process of accretion and slowly dwindling in its mass. And in so doing, it generates an enormous temperature, which is about 100 million degrees, which is hot even by astrophysical standards, by the standards of the center of our sun, which is only about 10 million degrees, or about a tenth that value. And this process may actually explain the origin of certain types of strange white dwarfs that we've seen in nature that are highly magnetic, that have a magnetic field so strong it's millions of times the strength of the magnetic field of the Earth, or even greater. And we believe that this process can explain the origin of those magnetic white dwarfs. I think to us the biggest challenge is the fact that sometimes we become so ensconced in our way of thinking about a problem that we could be sitting practically on the solution and not even see it. We are sort of thinking inside the box as opposed to thinking outside the box. In some cases, we don't even know the box is there to be thinking outside of that range of ideas. And when we're limited in our thinking, it really limits our ability to ask and resolve questions if you're not even asking the correct questions. That's probably, I think, the biggest challenge that we face. The ability of high-performance computing to enable researchers to discover things that they would never have normally had thought about, I think, is a very exciting enabler or part of science that's enabled by high-performance computing. To give an example of this, in some early days of thinking about supernovae, everyone was modeling these supernovae in a kind of spherical kind of way, and just by changing their thinking in the computer model, by making things a little bit less symmetric, an entirely new model or mechanism for the explosion of these stars was discovered. And that kind of thing goes on all the time in high-performance computing. It's the discovery the discovery potential of high-performance computing that enables us to expand our box and to think outside the box.